we're going to introduce a new equation to solve for voltage. So, imagine this electric field. And we also have the tree example again. With the falling apple from it. And gravity is also a field. The electric field here is going to be 10 newtons per coulomb. And we're going to round the electric field for gravity, or not the electric field, but the field for gravity, which is 9.8, and we're going to round that to 10. So it's 10 meters per second squared. And we're going to have a point charge right here. And this is going to be point A, and this is going to be point B. This we're going to call 0 meters, because this is like the ground, or where potential energy is 0. And this we're going to call 4 meters, because it's 4 meters away. Now the new equation I'm going to introduce is this. The voltage difference between A and B, which if B is ground, is just the voltage at A, which we talked about in the last video, is the difference between the two voltages, and is also equal to the integral from A to B of the electric field at each point and the unit length you traveled at each point. Now this is really complicated looking. It's really complicated looking. But think about it. You're multiplying electric field times length. You're multiplying newtons per coulomb for electric field times length, which is meters. And you want to get joules per coulomb. Newton meters is joules, so Newton meters per coulomb is the same as joules per coulomb. So let's apply this equation right here to this problem. So we're trying to find the voltage difference between A and B. We go from A to B. A is at 4 meters, B is at 0 meters. It's in the opposite direction. We're moving from A to B. So we're going to call it -10 in terms of dl. We solve this integral and we get 40 volts. Just like the last problem, don't worry so much about sign. Find the magnitude and then look at the arrows and determine what you think the sign would be. It's easy to tell that this point right here is at a higher voltage than this point right here, because just like right here, this point is at a higher potential energy than this point right here. So we know that the voltage here is higher than the voltage here. So we know that VAB must be positive. Apply this equation. Just plug in the values, don't worry about the sign. Get your answer, and then figure out what the sign is. Now, the cool thing about this is, look at it for the tree example. You want to find the voltage right here. This is A, this is B. You can either apply this integral from right here to right here instantly, just straight line, or you can move all about. You can move here, look at the change in dl. You go here, 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 and you end up here. So just the displacement matters. So any way you move doesn't matter. Just the start and the ending location. You're probably not going to be tested on this equation exactly, But I introduced this equation because I want to teach you a new concept. First, here's a term: equipotential surface. We introduced this in an earlier video, and it is that all points are at the same potential or voltage, which means that an equipotential surface will have the same voltage all around that surface. And I'm going to introduce another concept, and that is that the inside of a conductor has the same potential at every point in the conductor. So let's draw the spherical metal object, which is a spherical conductor. And we know that the radius of the sphere is R0, because we're going to make this general so we can apply it to other things. And that is, we go farther out, we're going to call this R. And we know that the charge of the sphere is Q. So, remember from the previous video, we know that voltage is equal to K times Q over R. R being this, Q being the charge of the sphere, K is a constant. But look at this theorem we just introduced. The inside of a conductor has the same potential at every point within the conductor. And the conductor is an equipotential surface. But why is this? Let's say we have the sphere, right? And it has a positive charge. And charges can move freely around the sphere because it's a conductor. So, if it has a positive charge, all of the positive charges are going to get as far away from each other as they possibly can. Because likes repel. Which means that in the conductor, there is no electric field. We went over this in the very first video. We talked about Faraday's cage, where conductors can't have electric fields in them. So looking at this equation right here, if there's no electric field in the conductor, then voltage change is going to be 0, because E0, you integrate E, the result is 0. So there's going to be 0 voltage change in the conductor, which makes this true. So let's draw a graph. On the y-axis, we have voltage, which tells us the voltage as R increases. So R at 0 is at the center of the sphere. We go to R0, which is the very surface of the sphere, and we continue through R. And we get this result right here. And that should surprise you. Why is this a flat line? This is because this is flat. I know it's not flat, but it's flat. Okay, it's flat. So, this is flat. It's because voltage at everywhere inside the sphere, the conductor, is the same voltage. Because electric field in the conductor is 0. But once we get outside of the conductor, this equation takes over. So this slope is voltage equals K times the charge of the sphere over R, as R increases. But how do we determine what the voltage of this right here is? The voltage at this point right here is the voltage directly at the surface. And the surface radius is R0, so this voltage is equal to K times Q over R0. And this is how you determine the electric field in conductors, or the voltage due to conductors. Now we're going to introduce a new concept. Imagine we have 3 charges. Just like I said before, potential energy, you need a base, you need what ground is, you need what potential energy of 0 joules is. And that is if all these charges are an infinite distance apart. So if you get a question on your test that asks you, what is the potential energy of these charges? Here's how you solve it. Potential energy, which we define as U, that's the variable we call it, is equal to K, 9 times 10 to the power of 9, Q1, Q2, over the distance between R1 and R2, plus Q1, Q3, times the distance between charge R1 and R3, plus Q2, Q3, divided by the distance between these 2 charges, R2, 3. This tells us if we put all these charges together, what is the potential energy going to be? This tells us the potential energy of all these charges. And let's say instead of having 3 charges, we had 4 charges. We'd have 6 terms because we'd have Q1, Q2, Q1, Q3, Q1, Q4, and Q2, Q3, Q2, Q4. Because each charge has to have a like term. So if there are 4 charges, we'd have 6 terms. 3 charges, we only have 3 terms.